We're going to begin discussing the graph of three-dimensional equations. And most of the time when we have a three-dimensional equation, it's going to contain all of the x, y, and z variables. However, at the beginning of the discussion, we're going to start with the easiest possible scenario, which is when one of those three variables is missing. So if one of the variables is missing, that means that the missing variable is going to be able to roam free, and then the graph is going to extend in the direction of that missing variable. So let's look at a quick example. So just to remember how we did this in algebra, if we were looking at the graph of x is equal to 2 in two-dimensional space, we knew that that was a vertical line passing through x is equal to 2. The y variable is missing, and so as you'll notice, then we are extending infinitely in the direction of y. X is held constant, and we extend infinitely in the direction of the variable that is missing. So similarly in R3, or in three-dimensional space, the only variable that is held constant is x, and then we're going to be extending infinitely in the direction of the two missing variables, which are both y and z in this particular case. So what we can do here is we'll graph x is equal to 2. Essentially, we'll start by graphing it in the xy plane, right? We have this same basic line in the xy plane. We're extending infinitely in the direction of y. So this is the same line, x is equal to 2, that we just graphed over here. We're graphing it in the xy plane, which is the floor of R3, as opposed to looking at it straight down from this R2 graph. So these two graphs, basically, this is the same as this, but just looking straight down on the floor here, as opposed to coming out into the first octant to view it here. So, but we also need to then extend, since we are in R3, y is missing, so we extend in the direction of y, that's true, but we also extend in the direction of z, so we need to take this line and go up with it. This is actually going to end up being a plane. We extend infinitely in the direction of z as well as in the direction of y. The only thing that's held constant is x, and we expand in the direction of y and z. So let's look at another example. We'll first of all graph the equation x plus 2y is equal to 2 in R2, and then we'll see what that equation looks like if we were to graph the same exact equation but in R3. Again, R2 is two-dimensional space, so we'll use just our basic algebra principles here to graph this one. Let's subtract x from both sides and then divide both sides by 2 to get negative 1/2 x plus 1. And since this is in slope-intercept form, we can then say plus 1 is our y-intercept. And we'll go down 1, right 2, and down 1, right 2 to get a couple of ordered pairs in two-dimensional space to plot our line. And let's label these ordered pairs so that we can kind of be real careful with our part B here. So this is going to be 0, 1, 2, 0, and then 4, negative 1. So we've got 3 ordered pairs that we'll take a look at when we get into R3. So here we are in R3, and R3 has this xy plane. The floor is the xy plane that we have a top-down view on, like this. This is the floor of R3. So we're going to try to duplicate this image, but in the floor of three-dimensional space, right? So we'll say that since our y-intercept in R2 was 0, 1, we're going to come in here and say 0, 1, 0 for the x, 1 for the y, and since we're in the floor, z is also 1, so 0 for the x, 1 for the y, z is 1, gives us the R3 equivalent of our first ordered pair, but now it's an ordered triple because we're in R3. And then the next ordered pair that we're going to translate into our R3 floor is 2, 0, right? So we had 2, 0 before. That's 2 in the direction of x, 0 in the direction of y. So we'll say 2 in the direction of x, 0 in the direction of y, and we're in the floor, so the z-coordinate is 0. So this is going to be 2, 0, 0 is that ordered triple. And then let's make this ordered triple in the floor of R3. So 4 in the direction of x, -1. So we go 1, 2, 3, 4 in the direction of x, -1 in the direction of y. So we get down here. This is the ordered triple 4, -1, and since we're in the floor, the z coordinate is 0. So we'll graph this same line in R3 in the floor, which is the xy plane. But since we are missing the variable z, right, z is missing, that means we're going to extend this line infinitely in the direction of z. So we basically just fly this up and extend it in the direction of z. So we go up like this and down like that. So because we have that missing z variable, this graph is going to correspond to a plane. Now I have jumped over to GeoGebra here to illustrate the to check our answer basically. And so here I have the 3 ordered triples that are in essentially the floor, the xy plane. So we've got our xy plane here. I'm looking at the first octant. And the 3 ordered triples have been plotted here. Notice that in GeoGebra, in order to graph a point or an ordered triple, you need to use a capital letter in order to get that to graph. If I use a lowercase letter, it's going to graph a vector. And so in order to get a ordered triple, we need that to be a capital letter, not a lowercase letter. So I'm going to delete this because that's giving me, see, that gave me the vector there. So I delete the vector and use capital letters to get ordered triples. So the equation that we were checking was x plus 2y equals 2, and we put that in, and we see that we essentially get a line passing through all 3 of those ordered triples and then extending in the direction of z, extending infinitely in the direction of z. If we were looking down on that xy plane, we see that we have that straight line through those 3 ordered triples, and that would be our 2-dimensional coordinate system. But when we kind of fly up like this, we can see that it extends infinitely in the direction of z. So it's a good way to kind of check our answer in using GeoGebra.